I think that's it. All right, now with that, I'm going to go to this one next. Now, what you just wrote down, I would just add to what you just wrote. I don't want you to just recopy everything that's on here because this kind of does the same thing as what we just had. In the first energy level, all I've added really is the number of electrons. So for each energy level, write down how many electrons are at capacity in there. The first energy level has a room for a whopping 2 electrons. It's so close to the nucleus, there's not much room down there, and it's just one s. The s has room for 2 electrons. P has room for 6 if each of those orbitals have 2 electrons in them. So there's a total of 8 electrons possible in the second energy level. The third energy level has room for 18 because 2s, or not 2s, 3s, that's what I mean by I'm tired. I'm starting to say dumb things. 3s has room for 2 electrons, 3p has room for 6, and 3d has room for 10. Add all that together, you get 18 possible. Can you see a pattern? How many could exist, or would the n equals 4, the fourth energy level, how many would fit? Rohit, how many? No, you'll have another sublevel that will hold electrons, so it's going to be more. Come on, math people. First energy level is 2, second energy level is 8, third energy level is 18. How many in the fourth? There's a formula for it. I'm hearing you. Are you saying it, Neha? Yes, 32. Yep, it's 32. What's the formula? Okay. But it is 32 because S has room for 2, P has room for 6, D has room for 10, F has room for 14, add all that together you get 32. It is this formula right here. I know the 2's look like Z's in this font, but it's 2n squared. If you know what energy level is being asked about, 2n squared tells you how many electrons can fit into the energy level. And you can check that, sure enough. That's right. How many electrons fit into the n equals 5 then? Now it's easy.
No, it's not.
Well, and let me ask you this. S has room for 2, P has room for 6, D can fit 10, F can fit 14. How many would G hold? Just G. How many electrons? How many? 18, right. Because it goes 2, 6, 10, 14. It's going up by 4 every time, and it would be 18 electrons just in the G, so that the n equals 5 could have room for 50. 18 more than what the fourth energy level had. Yep. Now these energy sublevels, they need to be put into order. And you may remember, you will remember this when we talk about this if you don't right now. When we start ordering these things, we start close to the nucleus and work out. First energy level is closest, so it's the lowest energy. And then 2s, and 2p, and then 3s, and then 3p. But then you remember about the Ds. The Ds are a high energy sublevel. They're so high in energy that they actually overlap the next energy level's S. Have you heard of that before? You have. Any Chem 1 class, whether you were here at Troy High, at a different school, or even took it online, you had to have known that the S's, the D's will overlap the S from the next energy level higher. Take a look at this energy level diagram. It says in any energy level, S is always the lowest energy sublevel, and then P's and D's and F's. F would be the highest sublevel energy in an energy level. Now, I know this is kind of obnoxious, but this is a way that we represent how the electrons are arranged in an atom. Electrons always fill close to the nucleus, which is the lowest energy at the bottom of this thing, and once one energy sublevel is full, then you go up to the next one, filled in. Then you go up to the next one, filled in, and so on, all the way up. The lines correspond with something. What are the lines on this thing? S's all have one line. P's have 3 lines. D's have 5 lines. What are they? Those are the orbitals, yeah. Each orbital has room for 2 electrons. So within sublevels, there's these orbitals. That's the various shapes that you saw. But yeah, this is a way of just describing how the electrons are arranged. Another way to describe how electrons are arranged is by giving the electron configuration. Electron configuration and this pretty much give the same information. This is a little bit more descriptive than an electron configuration is, but it's so clunky to have to write that electron configuration usually is what's used, just because it's streamlined. You just write an electron configuration like you'd write a word. Each line represents an orbital. Orbitals have room for 2 electrons. We use this thing and we represent electrons with arrows. You always put an up arrow first on a line before you put any down arrows. That's just the convention that we use, just so everybody does the same thing. I'll do this on the next place we land. Now this order of things, I tried to put, use different colors for the different energy levels. There's only one that's red up here, and that's the first energy level, because the first energy level only has the 1 orbital, or the 1 sublevel. The second energy level is right here in green. The third energy level is in blue, but you notice that in the third energy level, you see there's an intruder there. The 4s has kind of gotten in the way between 3p and 3d because we have that overlap. But check out the 4th energy level. I got to go way up there to catch the 4th energy level. There's a lot of intruders in the 4th. In fact, in the 4th energy level, there's probably more dissenters than 4th energy level. So just know that, yeah, as we go up in energy, the order of energy levels and sublevels, there's a lot of overlapping that happens. So you have to keep straight. You okay with this slide? All right, I'm going to skip this slide. I find it annoying. We've already done this slide. Now I want to just show you this. This is the way that we represent electrons. Now this has the electrons going left to right rather than up. But I think you can get the flavor of this. One of these 4 is the correct electron arrangement for nitrogen. And I'm having you draw on what you learned last year because I haven't given away the surprise. One of these 4 is not even nitrogen. Don't pick that one. Let me ask you that first. Which one is not even nitrogen? D is not nitrogen. There's 8 electrons represented in D. Nitrogen only has 7. Okay? So the electrons in nitrogen are not arranged like this. I'm thinking that you have to choose between A and B. Right? You would choose B if you thought that when you get 1s, you go up and down, and then it's full. So you go to 2s. Up and down, then it's full. You go to 2p. Up, down, up. Now you have all 7 accounted for, and that's it. However, what did you learn about filling the sublevels that have multiple orbitals in them? Put 1 up in each before you pair any up. Yep. Again, I had mentioned this earlier, this is not a design that humans came up with for how we think atoms should behave. This is what they do. So A is the correct answer on this, and the story behind that is called Hunds Rule. I don't know what Hund's first name was. I think it was German, like so many of these people. Germany was a real hotspot for this modern physics thing. But Hund said, now, both in my 4th and 5th hour, I got kind of a reaction from the class when I used the word degenerate. The word degenerate, you know, we're talking about people is like an insult. Hey, are you degenerate? Oh, can you call me that? But the word degenerate in a science context just means you have things that have the same energy. And they're virtually interchangeable. Like the three p orbitals, one's along the x, one's along the p, one's along the p, okay. One's along the x, one's along the y, and one's along the z-axis. It doesn't matter which one gets filled first, they're all the same. So they're what we call degenerate. So the degenerate orbitals, which is where you have the p's, d's, and f's, they have multiple orbitals in them. Put one electron into each, and then start pairing electrons together. Nice weekend. Okay. Hunds rule is important when you're asked about how many unpaired electrons an atom has. For instance, nitrogen has 3 unpaired electrons. And that's going to determine some things about the way nitrogen atoms behave. If I were to ask you, just take another element on the periodic table. How many unpaired electrons would an atom of titanium have? Ti number 22. You wouldn't have to do this whole thing. Oh, not that. I don't think you'd have to start at 1 and go all the way up to the 22nd electron. I think you could just kind of look at the periodic table and tell. You know, where are the last electrons in titanium? What energy sublevel? It's a D, which D? 3D, 3D. Remember, the D's have that overlap, and in the 4th row, there's 4s, 3D, and then 4p. So the last electrons are in 3D. All the electrons up to 3D had to be paired up because they were filling their energy sublevels. Yes? So the only thing you have to look at when you're asked about unpaired electrons is the last sublevel that has electrons. So titanium has 2 electrons in 3D. How many unpaired? Both of them are. You'd say that there's 2 unpaired electrons. Yep. Because 3D for titanium would look like that. And where everything else is full with an up and a down on each line. Okay. And the last thing that we'll take on today is electron configuration. Electron configuration is written like this, and this tells the same thing that the energy level diagram or the orbital diagram shows. It tells you what energy sublevels contain electrons and how many. So rather than using arrows, we just write numbers. The orbital diagram with the arrows is a little bit more descriptive, but this is fine. I mean, this is well accepted to use this. Fluorine has 9 electrons. They're arranged starting at the lowest possible energy close to the nucleus. 1s is full with 2 electrons, then it goes to 2s, that's full with 2 electrons, then it goes to 2p, and there's only 5 electrons left, so they all will fit into 2p. And so that's our electron configuration for fluorine. How many unpaired electrons? 1. Right. Okay, now we have an electron configuration of potassium given. Potassium has 19 electrons. Atomic number is 19. The 19 electrons in potassium are arranged like this.